So dealing now with the omission method of teaching relativity. The way that Einstein's relativity is taught is to omit mention problems and difficulties whenever possible. This works into deceiving the student into thinking they understand the subject when they don't. An example of this omission method will now be looked at. This is a picture of Sean Carroll. He's an American theoretical physicist. So we'll now play this video of him.
To really understand relativity, the secret is to take a truly four-dimensional viewpoint. We can say that the universe is made of 4 dimensions. There is 3 dimensions of space and 1 dimension of time. What we mean by that is that to locate something, you need to give me those 4 pieces of information. Where are you in 3-dimensional space, and when are you in 1-dimensional time? So if you want to meet somebody at 5 p.m. at a certain location, you need to say where that location is and give the time. Nevertheless, we tend to think in terms that say that time and space are very different. We tend to think of the universe as a 3-dimensional universe with stuff in it. We tend to think that reality is a 3-dimensional thing, and that 3-dimensional thing happens over and over again as a function of time. As time passes, 3-dimensional reality evolves. But the 4-dimensional point of view, which is optional in a Newtonian viewpoint, becomes absolutely necessary when relativity comes along. So let's think about what that means. In 3 dimensions, we have points. We say, here's a particular point in space. It's different than all these other points. In 4 dimensions, in what we call space-time, instead of points, we have events. So if you say this particular point at 6 p.m. on October 25, that one moment of time, that is an event. So event is not a place, nor is an event a specific time.
So I just want to add, he is using the event as being a point in 4D space-time, 4-dimensional space-time. Others talk about things like this in a different way to what he's dealing with it.
It's crucial that we mean, not that there's an important event. An event is not a happening, either a glamorous event or a non-glamorous event. It's not something that occurs, it's just a location in space-time. Just like we have locations in space, if you have a location in space at a specific time, that's what an event is. And then space-time, the 4-dimensional reality of our universe, is just the collection of every event. Just like space is a collection of an infinite number of points, indexed by the 3 dimensions of space, space-time is a collection of an infinite number of events. What we want to do is to understand those events and internalize it so well that we can throw away the division of space-time into space and time, to treat it as one truly 4-dimensional thing. This is a very difficult trick to pull off intuitively. We're not used to thinking 4-dimensionally, but we can train ourselves to do better and better.
That trick can mess things up. Let's put that issue aside and just move on.
The real difference here is the difference between the Newtonian view of the universe and the Einsteinian view of the universe. They both have a 4-dimensional space-time. In both Newton and Einstein, you need 3 dimensions of space, 1 dimension of time. The difference is that they divide space-time up into space and time in very, very different ways. If you were Isaac Newton or any of Newton's followers, you thought that space and time are separate and they're both absolute. So when we say that space and time are absolute, we mean that they're given, we know what they are. There are no choices to be made. It's not up to us. Different people don't have different kinds of space or different kinds of time.
That is a misrepresentation of Newton.
So in a Newtonian point of view, you would say, here's an event, here's a point in space at a moment in time, and for any one event, there's something called the present moment. That is to say, to any one event, there's a whole three-dimensional slice through reality, and that moment is the same time as this event. It is all of space at one moment in time. It is a notion of simultaneity. What set of events happen at the same time as this particular one event? So the picture in your mind is of a four-dimensional universe, and time slices the universe into moments of time. In a Newtonian point of view, both time and space are there given to us. Any one moment has a present, everything before it is its past, everything in front of it is its future. Now, whenever we get to these confusing issues of space and time, it is very helpful to ground ourselves by thinking operationally. In other words, by thinking about clocks. One way of thinking about time is that time is what clocks measure.
So that is all a misrepresentation of Newton. Newton has both absolute time and relative time. If you look at, say, the Stanford Encyclopedia of Philosophy, he says Isaac Newton founded classical mechanics on the view that space is distinct from body and that time passes uniformly with regard to whether anything happens in the world. For this reason, he spoke of absolute space and absolute time, so as to distinguish these entities from the various ways by which we measure them, which he called relative spaces and relative times. So Newton has relative time, and he does not confine himself to just talking about absolute space and absolute time. So Newton's treatment of time is much more complicated than how Jean Carroll is presenting it to be. Jean Carroll's presentation that it is relative time of Einstein versus Newton absolute time is just dumbing down of the full complexity of the subject. As an educator, it can be seen that he wants to present something that is easy to understand to those he is teaching. But what he is doing with this simplifying is of a complex subject, he is falsely representing that subject. That can be seen as to why the educators want to omit the full complexity of a subject. They want to dumb it down and simplify it so that those being taught can understand it. But what is being taught by this method of omission is false, i.e. being led to understand something that is false by this method. This method of falsification by omission continues throughout the rest of his talk.
So when we say that in a Newtonian space-time, any one event has this three-dimensional slice associated with it, the whole universe at one moment of time, what you should be asking yourself is, how would I construct that using clocks? What would I actually do to measure this concept? Rather than taking this God's eye view of the whole universe, what would I build and what would I write down in my notebook? There's a great book by Peter Gallison, who's a historian of science, called Einstein's Clocks and Poincaré's Maps. Einstein, of course, you know of. He is the founder of relativity. Poincaré you've heard of in the context of the recurrence theorem. He was one of Europe's leading thinkers at the turn of the century, around the year 1900. And he did a lot of work that was prior to Einstein, basically laying the groundwork for what we currently call relativity. Poincaré was very interested in the symmetries that underlie the theory of relativity. The symmetries that say, no matter where I am, physics is the same. No matter how fast I am moving, physics is the same. And no matter what direction I am pointing in, physics is the same. It was Poincaré who put all those symmetries together.
So Carroll now seems to be appealing to this man in this picture of Henry Poincaré as giving support for Einstein's relativity. In the way that Carroll is presenting Poincaré, it is like Poincaré is supporting Einstein's special relativity, but as per Wiki, it gives a rough guide. Wiki is not 100% accurate, but it gives you a rough idea what's going on. It says Poincaré's work in the development of special relativity is well recognised, though most historians stress that despite many similarities to Einstein's work, the two had very different research agendas and interpretations of the work. So basically really saying Poincaré's theorising is similar to Einstein, but it's not precisely the same. So Poincaré's theory is not the same as Einstein's, though it is similar. Carroll is not pointing that out, and so Poincaré's work does not really fully support Einstein's theory. Muon, Carroll, is committing omission once again, dumbing it down to give what can be interpreted as a false representation that Poincaré's work fully supports Einstein when it doesn't. All these things, Poincaré, etc., are being presented with like they fully support Einstein's relativity when they don't. No mention is being made of the difficulties, so as to present a false impression there are no difficulties. It also leads to the priority dispute if you introduce people like Poincaré, which should really be mentioned, and Wikipedia given a rough outline of that as well. Albert Einstein presented the theories of special relativity and general relativity in publications that either contained no formal references to previous literature or referred only to a small number of his predecessors for fundamental results on which he based his theories, most notably to the work of Henry Poincaré and Hendrik Lorentz for special relativity, and to the work of David Hilbert and Carl Gauss, Bernard Riemann and Ernst Mach for general relativity. So really you've got a priority dispute with all these different people over the different parts of Einstein's relativity. In the case of special relativity, you've got Poincaré and Lorentz. Did they come up with special relativity before Einstein? And that is a priority dispute there. And no doubt Carroll didn't want to touch on that, so omits even mentioning it. Continue with his talk.
In Gallison's book, Einstein's Clock and Poincaré's Maps, he makes the point that we think about Einstein and Poincaré as these very abstract thinkers, people who are concerned with the very essence of space and time and reality far removed from our everyday lives.
And did these abstract thinkers, i.e. Einstein and Poincaré, agree? I think not. So still trying to give false impression that Poincaré supports Einstein. Continuing.
But in fact, Einstein worked in the Swiss patent office, and Poincaré worked as the president of the French Bureau of Longitude. Remember, the problem of longitude, one of the leading issues in the nature of time, tried to make people build better clocks to figure out where we are on the surface of the Earth. Poincaré played a big role in helping people try to figure out what longitude they were on, how to draw maps. And Einstein, in his patent office, he wasn't just looking at any old gizmo. At the time, in the early years of the 1900s, one of the most important kinds of gizmos to patent were clocks.
It is thought that Einstein might have got his ideas about physics from reading patents while he worked on the patent office, but Einstein never seemed to give enough details about that. So it's another issue to be argued over.
The point is that that was a time when transportation between cities became easier and easier. It used to be that every different city had its own time zone. You would just have the actual time that was associated with where the sun is above you in the sky. But once transportation and communication became easier, it became interesting to sort of relate the times in one city to other locations. Even within one town, it was important to synchronize your clocks. So many of the patents that Einstein actually looked at were for better and better clocks and methods for synchronizing the clocks. Gallison's argument is that despite the reputations of Einstein and Poincaré as very, very abstract, deep thinkers, they were both heavily influenced by their down-to-earth day jobs, by the need to understand maps, pictures of space, and clocks, measurements of time. When you want to think about space,
and if I'm noting that there's nothing in any of that about abandoning the concept of absolute time. You can still look at things from a Newtonian perspective of keeping absolute time. He's not mentioning that.
so to make sense of Newtonian spacetime, imagine actually constructing that slice through the universe that we call the present moment. What you might imagine doing is building a large robot army. Each robot has a little clock on it, and they all have spaceships. So even though we're being practical, this is certainly a thought experiment, but that's okay. Imagine you have a lot of robots and you can send them anywhere in the universe. So your trick to constructing what you mean by a single moment at one moment in time throughout the universe is to synchronize the clocks. So you bring your robots together.
Right. Yeah, he says synchronize the clocks, but omits to say how to synchronize those clocks. There are synchronization problems that he's able to gloss over.
You set their clocks to read the same amount, and then you send them throughout the universe. Imagine we could put a robot with a clock at every point throughout space. We know that the clocks read the same thing because when they were here next to us, we synchronized them. So now you basically have a label at every point, at every event in space-time. You know where the robot is, so you know where it is in space. And it has a clock, so you know when it is in time. So basically, through this thought experiment, you can try to make real Newton's absolute space and time. You can say, what I mean by the universe at one moment is simply the set of events where all of my robot clocks read the same time. When they all say 6 p.m. November 5th, that is a moment in the history of the universe. The problem is that Einstein figured out that this technique doesn't work. That even as a thought experiment, you can't take robots, synchronize their clocks, and send them all throughout the universe.
He still omits to talk about the synchronization issue. His thought experiment is really based on a certain way of synchronizing clocks. He's not even going to talk about different ways of synchronizing clocks.
In relativity, in Einstein's point of view, there is no such thing as one moment of time all throughout the universe that everybody agrees on. To Einstein, space and time are combined into space-time, but space by itself and time by itself are not absolute. They are relative. That's why that word is attached to this theory. What you call space and what you call time will be different for different observers.
It's all still limited on the synchronization issue.
The clock doesn't read the same anymore. That's not a fault of my robot, Einstein says. That's a fault of space-time itself.
Fault of space-time itself, or really it's still the synchronization issue of clocks going out of synchronization.
This is the best way, I think, to conceptualize the difference between relativity, Einstein spacetime, and Newtonian spacetime. If you send out clocks following different paths through the universe and bring them back, they will have measured different amounts of elapsed time. If you're on a spaceship yourself and you're not firing your rockets or anything, you're just floating through space on some constant trajectory, either standing still or moving. Einstein says it doesn't matter whether you're standing still or moving. There's no absolute way you measure that. But you send out little probes. You send out little satellite robots, satellite spaceships. They both have clocks on them. They started synchronized. They go out exploring. They come back. Einstein says they will always be out of sync. It's not optional. It's not that your robots aren't good enough. It's not that there's a technology failure. It's that the amount of time elapsed on a different trajectory through the universe depends on how you move through the universe. And it works in a very consistent way. Namely, any time that you're moving on a crazy path through the universe, a curved path where you're firing the rockets, going at high velocities, and then coming back, when you come back, you will always have measured less elapsed time. The way, Einstein says, to maximize the amount of time spent in between two events in space-time is to do your best not to move, or to, equivalently, move at a constant velocity. Acceleration, curved paths through space-time always decrease the amount of time that your clocks measure.
So he emits out of sync, but saying optional, etc. makes no sense.
Now this is not just abstract nonsense. This is not just some theoretical speculation. It's a deep, profound idea. We're saying that there is no such thing as one moment spread throughout the universe that everyone can agree on. We're saying that what time it is at one point depends on who does the measuring. That's a deep fact.
I disagree with what he claims as fact.
But it's also experimentally verified. One of the most dramatic and immediate experimental verifications comes from the idea of a muon. A muon is an elementary particle. It's like a heavier cousin of the electron. The electron, of course, plays a crucial role in atoms. Muons don't play a crucial role in anything because they're heavier than electrons. They decay very, very quickly. The lifetime of a muon is about 2 microseconds, 2 millionths of a second. So if you had a muon right here, it would decay into pions. Pions decay into muons, which then decay into electrons and other particles. So muons, in some sense, are a clock. They're not a very good clock, but if you have a large collection of muons, over half of them decay every 2 millionths of a second. So by looking at how your collection of muons diminishes over time, you're essentially measuring how much time has passed. From measurements in the laboratory, we know that the lifetime is about 2 millionths of a second. Nevertheless, we find that we can discover muons here on Earth that came from cosmic rays in the sky. In fact, this was the way that muons were first discovered by Carl Anderson at Caltech. He was measuring cosmic rays, and he measured the existence of this particle that looked like an electron but was much heavier.
I disagree that it is experimentally verified. There is an issue of underdetermination, and the Stanford Encyclopedia of Philosophy explains that as at the heart of the underdetermination of scientific theory by evidence is the simple idea that the evidence available to us at a given time may be insufficient to determine what beliefs we should hold in response to it, which really means experiments can be interpreted by more than one theory. And that's another issue he's not mentioning. He's not talking about underdetermination, just something else he wants to omit talking about. So I'm ending this talk here. His method is the same as most educators for teaching relativity. It's to gloss over things, not provide sufficient details, and so enable those who have been educated to get a false impression. The educators do this because it then makes teaching the subject easier. If, for instance, the educator mentioned the priority dispute issue, with relativity, then the student might then start realising what was being taught was dubious. They might criticising what's being told them. They say, oh, there's this issue of priority dispute. Maybe Einstein didn't get everything right. Maybe it was Poincaré got it all right instead. And all these other issues which suddenly spring to attention to the student if the student's informed about these issues. So this method of omission acts as enabling the mainstream education to just keep sweeping certain things under the carpet. They dumb down teaching of relativity, don't even mention the difficulties, and they have an easier life than teaching the subject. But it's given a false impression of the subject to the students. Finn, thank you. That's the end of this talk. Cheers.